Okay, thank you, James, for the introduction here. Good morning, everyone, again. We're going to talk about something different here. This was already stated. Micro-LED array-based optical links that enable ultra-low energy interconnects. And this time we're thinking below a picojoule per bit. Before we dive in, just by a show of hands, as far as I can see against the spotlight here, who has heard of our approach by now? Okay, we do have a few hands. Well, we'll be a few more people by the end of this talk, so let's get started. In optical networking, we're not new to the concept of reducing energy consumption. We've started doing this in the 90s in the long-haul networks and then kind of moved through all the way metro access, fiber to the home. We've done it inside the data centers for a while, but now we're looking at the chip-to-chip communication inside of HPC systems and memory disaggregation, all the different topics that we're talking about throughout this show. And it's good to think about a couple of things that are particular to kind of short-reach chip-to-chip communication. One is, as Alan was also mentioning, as you're driving longer distances on copper interconnects, you're actually spending a lot of the power, disproportionate amount, in driving the links, not the processing. So replacing that with optical interconnects makes sense. And the other thing is, inside the processors actually run slow and wide buses, 1 gig, 2 gig, maybe 4 gig. So what is a good technology suited for that in the optical domain? Because in the networking domain, we've been focused on muxing up, going higher and higher speed per lane, reducing the number of laser sources, but that's not necessarily what's going to really help us in the short-to-reach communication. So we took our inspiration from the microdisplay industry. Microdisplay industry, AR, VR, is driving great progress. We can now put a few million micro-LEDs in a small display, a little bit more than a square inch, and this is done at very low power consumption. So wouldn't it be great if we could use that approach? And we don't need millions of pixels, we need a few hundred pixels. Wouldn't it be great if we could use that for communication? But the challenge has been so far, micro-LEDs and LEDs in general, they're known to be slow. I mean, lighting industry, that's just CW. If you're going to micro-displays, then you're looking at frame rates, or you're looking at megabits. Well, that's where we dug in deeper and managed to work the epi and the quantum well structure to actually make micro-LEDs run at up to 10 gigabits. We've just shown 14 gigabits in the lab. So now we have this micro transmitter here. This is, as you can show here in the center. See, it's very small, 5 to 8 micron side length. We put it on a 50 micron grid. The reason it's shown in a hexagon is because that's the best way of packing circular shapes into a larger circular shape. You have a vertical emitter now. You can collocate the driver right underneath. The LEDs are grown on sapphire. It's gallium nitride. They're transferred over to CMOS. And now you have a two-dimensional array as a transmitter. The transfer technology comes from the microdisplay industry, so that is getting worked by a large industry with massive investment, and we can leverage that. And then we couple the vertically emitted light into a bundle of fibers. This can be imaging fiber, or this can be lighting fiber, like lighting fiber as you have in a gooseneck. This is on the same grid. This is 50 micron fiber diameter with mostly core. It's a very thin cladding, 1 to 2 micron. And now you travel across. This is, as opposed to most of the communication which happens in the infrared, this one happens in the visible light. This is actually, we're using blue light 425 nanometer. This is, of course, it's not a laser, so it's highly multi-mode, plus minus 5 nanometers. So the reach is limited. The reach is limited by dispersion to about 10 meters. But 10 meters is actually plenty for chip-to-chip communication. It works inside the rack. It works to the adjacent rack. It will never go across the data center. So that's not the intent here. And then on the receive side, there's more good news. Silicon absorbs 425 nanometers, so blue light, visible light, extremely well. So it's extremely shallow depth, less than a micron, as you can see. So you can actually build your detectors natively in CMOS, and you can use a lateral structure. There's no co-doping needed. Usually in the infrared, you use silicon germanium or you use indium gas. So this is not necessary in this case. So now you have a very compact transceiver. You have basically with a few hundred, this one here that we're showing is 330 individual LEDs. They're in a hexagon, so this is about a millimeter in diameter. So you have a matching hexagon of PDs. Now you have a super compact transceiver that you can put natively on CMOS. What we're showing here on the right is the first chip that we're taping out. That's going to be a terabit, so the individual LEDs there run at about 4 gigabit per second. So it's a terabit link. And then you have the routing to the drivers. You have collocated on the PDs. You have the TIAs and the limiting amps. And then you route it to a parallel interface. That could be OpenHBI. It could be UCIe. UCIe is probably one of the promising approaches there going forward. So when we're looking in the same chart that Alan was showing, where we're comparing reach against the figure of merit of bandwidth density versus energy efficiency, you can see, as we know, in the short reaches, millimeter, kind of center right there up to a meter, that is today done all by copper. From there on out, it typically starts to switch to optical interconnects. The traditional ones down at the bottom, these are pluggable. Silicon photonics promises to push the efficiency somewhat higher. Alan was mentioning 3 picojoules per bit. VCSELs are also a promising technology and with a long reach. But what you get with microLEDs, you get that lower energy, but you get the limited reach. So basically what it does is it takes your copper interfaces and extends the reach to about 10 meters. So what have we actually done so far? Well, we just showed less than 1 picojoule per bit interconnect. This is using a first test chip. This was nothing special. This is a 4x8 array. So on the right-hand side, the black dots, those are individual LEDs with their collocated drivers. We have the PDs with the TIA and limiting amps on the other side matching to it. And then we ran individual links, and we could close the link. If we used a bit error rate of 10 to the minus 11, 12, we could drive the transmitter at about 0.8 picojoule per bit, at 0.5 for the receiver. So this is a little over a picojoule per bit, but then we could take down the drive energy on the transmitter and close the link still at less than a picojoule per bit total, albeit at a lower bit error rate. But again, this is an early ASIC. It's 130 nanometer node size, so this is nothing special. We'll improve on that. And the other thing I was mentioning, we've just shown in our labs 14 gigabit per second modulation on our LEDs, which is definitely a record, and we think we can optimize this further. I don't know whether if you're following us, you might have seen our announcement that we just acquired the the fab facilities from Nanosys, including their engineering team. So now we have our own reactor, so we can further optimize epi, quantum well structure, as well as the transfer technologies. So it's definitely exciting times. Right now as a company, we're located right here in the Bay Area in Silicon Valley. We're actually going to move into a new location in Sunnyvale. So where do we see this technology going? Well, as much as is it suited for parallel interconnects, we're actually driven by our kind of early customer partners to put it inside of active optical cables, because you still get the benefit of a much lower energy optical link, and then you have the other benefit of a standards-based ecosystem that you can plug into with millions of ports available. So we're looking at 800 gigabit Ethernet and 1.6 tera Ethernet active optical cables. But the real application we envision is in the chiplet domain, where you can have UCIe, OpenHBI, parallel interfaces on the chiplet side. You put your optical transceiver on that chiplet, interface to a host ASIC with the same parallel interface, put the two as a multi-chip module on a silicon interposer, and now you can interface directly to a wide range of processors or memory. And the holy grail, we think, is putting the transceiver directly onto the host ASIC. So this could now go directly on a GPU, a CPU, memory. It could be HBM, it could be DRAM, and eliminate any internal connection. So this is, of course, the most efficient application of this technology, but it will take some time to mature before people will be agreeing to putting this directly on their next generation GPU, for instance. Well, I hope I could get you inspired here by this new paradigm in optical interconnects that we think is coming. In summary, you can say, so this is truly low energy, less than a picojoule per bit interconnects are possible. Truly low latency, because this is all NRZ. There is no higher order modulation, because the modulation of the data rates of the individual lanes is relatively modest. It is very dense with the grid. So it's more than a terabit per millimeter. Millimeter is the beachfront, the edge of a chip, but it can be multiple terabits as we scale up the speed per lane. And it's also high temperature tolerance. We didn't talk about this much yet, but LEDs are extremely resilient. That's one reason they've taken over the lighting industry so fast, and they're getting into headlights for cars. They can easily run at 125 degrees Celsius, which is good when you're next to a hot processor. Actually, we've been running a batch now for more than a couple thousand hours at 150 degrees Celsius in our reliability lab, and no degradation. The reach is limited, so this about 10 meters. We could probably extend that somewhat, but we don't expect this technology to ever go, definitely not go kilometers. This is not the technology for this. It's highly cost effective because it leverages existing ecosystems, or it leverages the ecosystem of the microdisplay industry. It leverages existing fiber ecosystems that we can use as bundles. And it very seamlessly integrates with CMOS. It is fully compatible. This side. Thank you, and I'm happy to take a couple of questions.